Hello students, and welcome to this video in which we will be discussing the question, what is a limit? You may or may not, depending on how much time your pre-calculus teacher had for it, you may have already discussed limits already. However, you might not have. I hope that this video will serve as a good groundwork for just the foundations of what a limit is. In particular, I want you at the end of this video to have an idea of how to estimate the value of a limit using a graph or a table. Alright, let's get going. So the first thing I want to help you with is how to read limit notation so that you can look at a limit and know what it means. I have here the analytical description of a limit. That may or may not look like a bunch of gibberish to you, depending on what you remember or learned or didn't learn in pre-cal. But that's okay because I've put a verbal description underneath. Okay? I've translated this into common words, which you can do with pretty much every equation. Okay? So let's take a look at this verbal description. So it says if f of x, alright, so remember f of x is referring to the y value, the output of a function, and so if f of x is becoming arbitrarily close to a single number L, right? L then must be a y value because f of x is getting really close to that single number. It's a specific y value, and you can see those in the equations up above. Okay. Now, as we're saying, it's the f of x is becoming arbitrarily close. Well, what that means is that it's approaching that value very closely, but it's not necessarily reaching it. It might reach it, it might not reach it. Okay, you can think in terms of like asymptotes and things like that is where you've encountered this concept before. Okay, so f of x is approaching very closely to this number L, okay, so that's the limit part. That's what the limit means, getting arbitrarily close. As x approaches c from both the left and the right. X approaches c from the left is indicated by a little minus sign raised kind of like an exponent. So we have there the limit as x approaches c from the left for f of x. And then we also have x approaches c from the right, which is indicated with a plus sign. Okay, so if the y value is becoming extremely close to this particular number L as x approaches this value c, whatever x value it is, from both the left and the right, if we're approaching the same number, then we can summarize that by saying the limit of f of x as x approaches c is L, which is exactly how you read the part that I've highlighted in green. You read that limit notation as the limit as x approaches c of f of x equals L. Okay? That still may not make a whole lot of sense. So we're going to go look at some examples here. And particularly here, as I mentioned in this video, we're going to focus on being able to interpret them from a graph and from a table or numerically. So let's put a specific function and some numbers to it to help you understand all this gibberish that appeared before. Alright, so we're looking at a specific limit here, and you would read that as the limit as x approaches 0 of the function sine of x over x. Okay, so we're looking at a graph here of y equals sine of x over x. And we're interested in what happens as x approaches 0. Okay, we need to look at it from both sides, the left and the right. Okay, here's where 0 is and where I'll be approaching. I want x to get really close to 0. Okay, so as x approaches 0 from the left, that's what the little minus sign means. Okay, I want to know what's happening on the function. So if you follow that little arrow, if you're approaching that x equals 0 mark from the left, you'd be following up that direction. And the limit's asking, well, what is y approaching? What is y getting really close to as x gets closer and closer and closer to 0 from the left? Well, y is getting closer and closer to 1. Even though there's a hole in the function there, okay, it doesn't matter whether we actually reach that value of 1, okay, but we just want to know is y getting very, very close to that number 1. That's that arbitrarily close deal. Okay, we also need to check what goes on from the other side as x approaches 0 from the right. That's the little plus sign. Okay, so coming from the right would be following this arrow, okay, coming from the positive side. That's why we use a plus. What is y getting really, really close to? Okay, well, as x approaches 0 from the right, y is getting arbitrarily close to 1. Approaching it, but maybe not necessarily touching. Okay, so notice that both of those are the same. When x approaches 0 from the left or from the right, y is approaching the same value, getting arbitrarily close to this single number 1. So I can say that the limit as x approaches 0 of sine of x over x is equal to 1. That is my estimate, and that would be correct. And so we know that as x gets really, really, really close to 0, then the y value of the function is getting really, really, really close to 1. Another way to look at this limit is using a table. A lot of times this can be more reliable than looking at a graph because I'm getting specific numbers at x values close to the 0 value here that I'm interested in. I'm going to center the table on 0 because that's what the x value I care about. What's the y value that goes with that? Well, I'd just have to plug in 0 to the function to figure that out. Sine of 0 over 0, well, sine of 0 is 0, and 0 over 0? That's undefined. Okay, we'll actually encounter this 0 over 0 multiple times as we go through calculus. We'll learn later that it's called an indeterminate form, which gives us permission to use a rule called L'Hopital's rule. And also 0 over 0 usually indicates that there's a hole in the function, as you saw in the graph on the previous screen. So I want x to approach 0, so I need to generate some values that approach 0 from both sides on my table. Now, what I'm about to write, don't write this. Okay, what people tend to want to do is they just want to fill it in like this. 1, 2, 3 on each side. But are those numbers getting really, really, really close to 0? Not really. So instead, write this. How about we start with some values very close to 0, like 1,000th and negative 1,000th, or 0.001. Then I can approach 0 by making the next values be 100th and 1/10th. Okay? Same on the negative side. Okay? If I use those values, now we're getting really, really, really close to 0, but not necessarily touching. Okay? So now to make it easier than just typing all of these separately in your calculator, a tip for those of you who use a TI-84, which we'll be using primarily in class, and a way to set up your table to make this easier is if you push second and then the window button, which is called table set, and you'll get a screen like this. If you change the independent variable from auto to ask, then you can manually type in the x values yourself, allowing you to create whatever table you want rather than the default table that the TI gives you of counting by ones. Okay. If you do that, let me just generate those values for you now. Okay, you get some values like this, 0.99833, then progressing to 0.99998, then to 0.99999. Okay, that's, wonder what that's getting really close to. On the other side, since this is an even function, you see that those values are symmetrical. If you want to see more decimal places, here is a screenshot of the table I used Desmos to create. And you can see what those full or more full decimal values are. They go on forever. But, okay, so to answer my question about the limit, I want to know as x approaches 0 from the left, what is happening to y? Well, y is getting really, really close to 1. Okay? 0.999999983 is very, very close to 1. Y is approaching 1, getting arbitrarily close, but not necessarily touching. What about the other side? As x approaches 0 from the right, okay, then what is y approaching? Y is approaching 1. Okay? As we move in from the right to the left, approaching 0, we're getting closer and closer to 1. Since those numbers are the same, again, we can say that limit is equal to 1. All right, so let's look at just a couple more examples so you can get a better picture. Maybe look at another function or so. Oh, but I did want to show you this one thing. Notice that I don't particularly care what happened at x equals 0, the fact that that was undefined. It didn't really matter. If that had said a value of 2 instead of undefined, or a value of 1,373 or whatever, I don't really care. The stuff in orange just doesn't matter. All I care about is what happens as x approaches 0, which is the values in blue on either side. What happens at 0, who cares? All right, now on to the next examples. These two limits present interesting twists that illuminate some important key points. In this first limit, we've got graphs of r of x and f of x given to us here. We want to consider as x approaches 1 on the function r of x. So I've highlighted x equals 1 on the graph there. And in order to evaluate the limit, as we've discussed before, I need to know its behavior as x approaches 1 from the left and also from the right. So let's consider first the left side. As x approaches 1 from the left, we're coming from this direction. What y value is r of x approaching? 2. Even though there's an open circle there, the y value on r of x is getting arbitrarily close to the value 2, even if it doesn't actually reach it. What about from the right? Well, that would be coming in from this direction. What y value is r of x approaching? It's approaching a y value of 1. But wait a second. Those two values are not the same. So we say that this limit as x approaches 1 does not exist because the function is not approaching the same y value as x approaches 1 from either side. Okay, so now let's look at the second one. Here we've got an interesting function. We've got a composite function, r of f of x. This could be interesting. I am interested for when x approaches 2. Okay, and so x is approaching 2, and x is right there. So x is really affecting, as x approaches 2, that's affecting f, not directly r. So I could really rewrite it like this. Okay, r of the limit as x approaches 2 of f of x. X is approaching 2, then whatever happens to f will tell me what value I plug into r. Note though, that this only applies if r is continuous at the value we determine for that limit. If it's not, we have a lot more in-depth analysis to do, and I'm not going to cover that in this video. Okay, so let's consider what the limit as x approaches 2 is on the function f of x. I need to consider as x approaches 2 from both sides. So here is from the left on the graph of f of x, and also from the right. What y value is f of x approaching in both cases? Oh, f is approaching 2. Now, that just happens to be the same as the x value. I should have picked a better graph. But, x is approaching an x value of 2, and as it does so, the function f is approaching a y value of 2. Okay, so that means that since that limit is equal to 2, oh yeah, and I want to point out again that that point right there, I don't care. I don't actually care what happens at x equals 2 for the purposes of the limit. All I care about is what's happening as x approaches it at 2 from the left and from the right. So I can now, since that limit is equal to 2, I can plug in 2 into the parentheses, and I just evaluate r of 2. r of 2, oh, that's right there. Okay, the value of r when x equals 2 is 0. All right, there we go. Those are those two limits. So hopefully that gets you a good start or a good refresher if you already learned some of this in pre-cal. And feel free to ask me any questions if you need it.